In this video, I'm going to talk a little bit about the, it's going to be a lot of naming, but also the chemistry of alkenes, so I've talked about alkanes so far, which are chains or rings that have a bunch of carbons that are single bonded to each other. And so that's an alkane. An alkene, so that's spelled like this. So ALKENE rather than the ALKANE. So these have double bonds in them. And so, as I said in previous videos, I'm following the organic chemistry textbook by L.G. Wade for this. And so, if I was following the book precisely, I'd be moving on to what's now chapter 4. But for this video, I'm going to skip ahead and cover part of chapter 7, which is about alkenes, because in chapters 4, 5, and 6, there is a little bit about elimination reactions and so forth, which have to do with double bonds between carbons. And so I thought I would just get this alkene stuff out of the way here before we move on to that. So like I said, this video is going to be a bit heavy on the naming stuff, but don't worry, there will be some other more interesting things as well. And so the first thing to look at is just the difference between a single bond between carbons and a double bond between carbons. And so the first thing to notice is that the single bond has 1.54 angstroms here, where this is 1.33. So the double bond is you know, significantly shorter than the single bond. We also have in the double bond that our our hydrogen to carbon bond here is a little bit shorter as well. And of course, the other thing to notice is that the bond angles between these different bonds here is larger. So in the single bonds is 109.6 degrees. Here we have 121.7 degrees, and then here is a little bit smaller. That's 116.6 degrees there. And that's just because there is a little bit of sort of pushing this hydrogen down because of these other hydrogens over here and these sort of steric clashes there. And so we have sp2 hybridized orbitals. So remember, in the alkanes, they are all sp3 hybridized. Here, the carbon is sp2 hybridized. And so it has more S character. And what I mean by that is, so if we look at the sort of P here, so when we have sp3, we can sort of put a 1 here. And so then the S character of that is 1 divided by sort of the sum of these two numbers, so 4. So that is 25% on sp3, where sp2, we put a 1 there, so it's 1 over, so we add up those two numbers, 3, and so that is I guess approximately 33%, so I should put the approximately there. But anyway, so it has more S character compared to the sp3 hybridized, so carbon to hydrogen sigma bonds. And so this is one of the reasons, well, this is kind of the reason that these carbon to hydrogen bonds are shorter on the alkenes than they are on the alkanes here. We also have that the carbon to carbon double bond here is shorter because, again, it has more S character than in the alkanes here. And because the extra bond, so because we have actually two bonds here, sort of draw the carbon atoms closer together. And so I use this figure in my introductory video, but this is kind of what's going on here, where we have the, so this bond here, this here, and this here are the sp2 there. So remember, we have s, which we can put kind of a 1 there, and p2. So we're bringing one s orbital and two p orbitals together. So we could make three different bonds. So one to a hydrogen, another to a hydrogen, and then the other to the carbon. But then that leaves a free p z orbital, which is what we have here. And so these will actually interact in lobes above and below the plane of the molecule here. And so we end up with these two lobes here. And so I didn't discuss this in the sort of introductory video, but the reason I put these in two different colors, and this won't really be important in this video, but it will be important in later videos, is that these are in different phases from each other. And so if we wanted to sort of turn this over 90 degrees and plot the phase of it, might say that this is in the negative phase. And so we have our line there. So that would be sort of going below the line, and then we go up to 0, which is what we will have when we sort of get right in the center here, and then it will go up into the positive phase here. And so that is a quantum mechanical effect. So I do have a long playlist about quantum mechanics if you want to get a little bit more into that, but that's just sort of what those colors mean. And so like later on when we get to like the Diels-Alder reactions and things like that, that will become more important. But I'm just sort of pointing it out now as just saying, just this is something to keep in the back of your mind here. But anyway, that is how these double bonds work, and these are called pi bonds. So the bonds between this single bond is called a sigma bond, and then these double bond ones are called the pi bonds. And so we do have sort of a lobe above and below, so it almost kind of looks like it itself is two different bonds, but this is just a bond between two electrons. It's just that quantum mechanical effect where the electron exists in this cloud that can have this node right here in the middle where there is zero density for the electron. But anyway, I don't want to ramble on about the quantum mechanics of it too much because we do have, as I said, naming to do. So the nomenclature, so remember with alkanes, we just called something that was a 2-carbon system an ethane. So here we just replace the ane with ene, so we have ethene, where the common name for it, and I'll put common names quite often here in these parentheses, so you'll often see this commonly called ethylene. If we're going by the sort of IUPAC nomenclature, this would be the sort of systematic name for it, but quite often you will see it called ethylene. But then we can also have alkenes in our cyclic systems, and that would just be like this is a 6-membered ring, so it's cyclohexene. So instead of cyclohexane, it's cyclohexene. Then same with propane, we now have propene, so we have this double bond here. And again, a common name for this is propylene, so you might see this called propylene quite often, where the sort of systematic name for it should be propene. Then, of course, when we get beyond 3 carbons, we can start having these isomers here. And so this one is called 1-butene because we are starting at the 1 carbon, so we have 1, 2, 3, 4, but you always put the 1 for the ene here where we have the starting one right there. And again, I have 2 names here because there was a sort of change in the nomenclature, and this change was something that actually happened when I was actually taking organic chemistry, because I remember my organic chemistry professor kind of complaining about it. But this is sort of the old nomenclature here. This is the new, but I put both of them here because you will still see it both different ways. But we have here one butene, so it's this. The one is referring to the first carbon on which this double bond is, and that is kind of the logic I think for why they changed it to this, because we have bute and this should be pronounced bute, like with butane, butene. Uh, so we pronounce that bute. And then this one here coming before the ene is sort of telling us that this one is referring to the ene. It's referring to the double bond on this. But then we can also see here we have 2-butene or but-2-ene. And so again we have 1, 2, 3, 4. And so here it kind of doesn't matter which direction we start counting from, because it will always end up on the 2. But we can see over here, and the double bonds always get this priority here. So you'd start counting from the carbon with the double bond there. Then we can see here something that's a little bit longer and has a few more isomers to it. We have 1-hexene or hex-1-ene, 2-hexene or hex-2-ene, where now we are starting on the second carbon. We have 3-hexene or hex-3-ene, where we are starting on the third carbon. And again, we get to a point where now it doesn't matter which side we start counting from, because it will be the same. And then, moving this double bond further along will just get us to something that is exactly equivalent to this one. And so we don't have further names for that. Then, of course, you can have multiple double bonds in a molecule, and so these are called dienes. You can have 3, which are called trienes, 4, which are called tetraenes, so on and so forth. And so we have here the 1,3-butadiene, or in the newer system, buta-1,3-diene. So we have 1, 2, 3, 4. So again, we put the numbers here for where it starts. So this is our first carbon because there's a double bond there. And then we put 3 there because sort of going in the direction that we were counting, this one starts at the third carbon right there. Then the next one we can do is the triene, and we have to get up to a 7-carbon chain for this. So we have 1,3,5 heptatriene or hepta 1,3,5 triene. So 1, 2, 3, 4, 5, 6, 7. And so we see we start here, we move along this way, and we get to the 3 and the 5. And so that's why we put the 1, 3, 5 there. And then this is to show, I guess, both that we have the tetraene, but also that this can apply to cyclic molecules as well. And so we would start, if we're sort of going around this way, we'd put 1 here, 2, 3, 4, 5, 6, 7, 8. And so that's why we have 1, we have the 1, 3, 5, 7 cyclooctatetraene, or in the newer system, cycloocta 1,3,5,7 tetraene here. And so, you could also go on to, pentaenes and hexaenes and things like that in larger molecules. All right, so then when we start adding some substituents here, so again, the double bond actually takes priority over substituents. And so what we see here, so we have the 2-methyl-2-butene or 2-methyl-but-2-ene. So this is in the center here. And so that isn't going to, on this molecule, tell us which way to start numbering from, but then we still start numbering from the substituent carbon. But if we go over here to this one, we see that we're saying 3-methyl. So we're not counting from this side. So we're not counting from that side. We're actually counting starting from this. So that double bond actually takes priority over a methyl group here. So this is 3-methyl-but-1-ene. So we start from this as the 1 carbon, then 2 here, then 3 there, then 4 right there. All right, then we can come down here. So we see we have this 3,6-dimethyl hept 2-ene. And so again, we start from this side. So we have 1, 2, and this is the 2. So this is taking priority. And so this is on the 3rd right here. This is on the 6th carbon right there. And so again, the double bond is taking priority over these substituents. And here's just a few more. So we have this cyclic one here. So we have the 2-ethyl. So we're actually starting right here, and then we put 1 there, 2, 3, 4. And so that's why we have 1,3 cyclohexadiene or 1,3-diene. So we start at the 1 here and we have the 3 here. And so this is to show too that we don't count around this way. Or we don't start from this one and then call this 2, because this has the substituent on it. So you might think, oh, well, we would start with this as 1 and put this as 2 and count around this way. But again, these double bonds take the priority. So we are not using that. We start here and we want to sort of go around it in the way that will get us to this next double bond even faster. And so we start with this as 1, this is 2, and so we have 2-ethyl. So this is our ethyl group here. So 2-ethyl cyclohexa-1,3-diene. So then again down here, just kind of driving this point home that this double bond really takes the priority. So this is a 1-ene. So we have 1, 2 here. We also have, I guess we could call this 1 prime, 2 prime here. So there are the same number of carbons, but we will start at the one that has the double bond right here, and then just call this an ethyl group right here. So we have 3, or so yeah, I put an ethyl group here. I accidentally named it propyl. So if this was propyl, we would want to actually put another carbon on it there, because propyl is 3 carbons. So if I just draw that in, we have a propyl group right here. So now this is 3-propyl hepta 1-ene. And so again, it's that thing, and the reason to show that is because this is actually longer now. So 1 prime, 2 prime, 3 prime right here. So this is actually longer than this chain here, but the double bond again takes priority here. And so we always start counting from the chain that has the double bond on it. All right, then we can have double bonds as substituents. And so alkenes as substituents are called alkenyl groups, which can be named systematically as ethanyl and propanyl, butanil, pentanil, hexanyl, so on and so on. However, ethanyl groups are commonly, in fact, you'll probably see it mostly called vinyl groups. And 2 propanyl groups are sometimes called allyl groups. And so, for instance, here we have this 3-vinyl 1,5-hexadiene. And so these have the same number of carbons, so 1, 2, and 1 prime, 2 prime here, so it doesn't matter which one we start from, but we will start from one of those because then we have a carbon with substituents on it. They're faster than if we started counting from right here. And so if we want to start counting from right here, then we can call this the vinyl group right here. So it's on the 3rd carbon right there. So it is 3-vinyl hexa 1,5-diene. All right, then we also can see here where we have this single carbon on a double bond there. And so we start counting from here, 1, 2, 3. And so that's why we have 3 methylene cyclohexene. So this methylene is what we will call this substituent right here. So we have 3 methylene cyclohexene. So this is why it's cyclohexene, and this is that methylene group right there. Then just another one to show here. So we have ethynyl benzene, and so we have this right here, which you might also see called like a vinyl group, so it might be vinyl benzene. And a common name for this is styrene, and so you might have heard of polystyrene. So I think that's often used in like packing peanuts and styrofoam and things like that. And so this is actually, so if you know anything about like polymer chemistry, this is a polymer, and it's made with these ethynyl benzenes as monomers. And so this double bond, and we're not going to talk about like the reactions of double bonds, but this double bond is what's used in the reaction to sort of link a bunch of these together. But anyway, that's why they call these styrenes right here. All right, another thing is that these benzene rings are often called phenyl groups and denoted with pH. And so if we have something like this, we might instead sort of just collapse this whole benzene ring down, or this phenyl group, into a pH. And so you might see things that look like this. And so if you know anything about like your amino acids, you'll know that there's like phenylalanine, and so that does have a ring like this on it, a benzene or phenyl group on it, and so that's why it's called phenylalanine. But anyway, so this would be called 2-phenyl 1,3-cyclopentadiene, and so again, we are counting using these double bonds with priority. So 1, 2 here, or we can put it over here, 1, 2, where this phenyl group is on the second one, then 3, 4, 5, and so that's why we have the 1,3 cyclo, and then this is a 5-member ring, so it is penta, and then it's two double bonds on it, so it is a diene. All right, then we can also start getting into these cis and trans isomers. So this is a pentene here, and so what we mean with cis and trans is just the way that the major or priority groups come off of the double bond. So cis means that they both go in the same direction. So we see this right here and this right here coming off of it in this, both in that direction, where trans means that this right here and this right here are coming off in sort of opposite directions from each other off of this double bond. So this one is the cis pent 2-ene, and this is the trans pent 2-ene. So cis means going in the same direction, trans means going in opposite directions. You can also get this in cyclic structures, and we'll actually see later in this video that you need these sort of large cyclic rings. In fact, you need at least like 8 carbons in the ring in order to get a trans bond in your ring. Otherwise, it just becomes too unstable that even at room temperature, they tend to break and sort of reform probably in a cis conformation. But yeah, anyway, we can get these trans bonds even in cyclic systems here. But then there is the problem of what happens if we have like multiple sort of priority groups on here. So I've been using that word priority, but here I'm going to actually be sort of defining what I mean by priority. And so we're going to use what's called the EZ nomenclature. So the E and Z come from the German word for, and I'll probably butcher the pronunciations, but zusammen and entgegen here, which Z means together, and this means opposite. And so we're again sort of using this sort of cis and trans, so together and opposite. But in this case, we're going to come up with some rules. And so we're going to look at each of the carbons on here and try to look at which of these things takes priority on this carbon and which of these things takes priority on this carbon right here. And this is something I'll bring up too in later videos, especially when we get to the RS sort of system for talking about like enantiomers and things like that. But here we can use it. So we will assign again, like I said, to a single carbon. And so atoms with higher atomic number receive highest priorities. So for instance, if we have something that has like hydrogen, so say we have a carbon here and we have a hydrogen, we have a CH3, we have an NH2, and we have an F. So that should be an uppercase F. So this is going to be our highest priority, then this will be our second, third, and fourth. And as we'll see in later videos when we're talking about the 3D structure of this, this is very important for this as what's called a chiral center, but we won't get into that. So right now we're just looking at the fact that fluorine is a higher priority because it has a higher atomic number than nitrogen, but that's the second highest priority because nitrogen has a higher atomic number than carbon, which is the third because it has a higher atomic number than hydrogen here. So if the bonded atom has the same priority, so now we're saying like, say we have a carbon here and we have like maybe two carbons, so maybe this is just an H and this is another F here, and these are sort of bound to three other things here. So now we're looking at this and we could say, okay, we know this is going to be the highest priority, but what priority order do we put these carbons in? And so then we look at the priority of the things bound to them. And so say this one has a further C bounded to it, but this one has only H's bound to it. And so this one has a carbon bound to it which is higher priority than any of these H's here. And so we would call this the second highest priority, third, and fourth. So we can look at a few examples right here where, like having this ethyl group here is higher priority than a methyl. Having a chlorine bound onto it is going to be higher priority than having like a carbon bound onto it. Having a bromine, because that's a higher atomic number than the chlorine, will be a higher priority, and so on and so forth. And so what we want to do is look at the priorities for what's bound to this carbon. And so we have this is higher priority than the chlorine. Then we look at the priority of things bound to this one. This is a higher priority than the hydrogen. And so the two things that are higher priority are pointing in the same direction. I put this red line here, by the way, just to sort of show that we want to look at the priority of the two carbons, the priority of things bound to the two carbons separately. But anyway, we see that the things with a higher priority are both pointed in the same direction. So remember, Z is for that German word that means together. And so the two things with higher priority are sort of in the same direction, they're together, and so we call this the Z isomer. Whereas if we have this higher priority one here, then this higher priority one opposite it, then we call this the E isomer here. And so this one we'd call the Z1 bromo 1 chloropropane chloropropene. And so we have this is going to be the 1 carbon, and this is going to be the 2 carbon here, but we see this is a 3 carbon ring right here. But we call it Z because this bromine is the higher priority here, and this is the higher priority there. And so it's 1 bromo, which is on the 1 carbon, and 1 chloro, which is also on the 1 carbon. But this Z is telling us about the stereochemistry of it. We're over here, the E is telling us that they are in opposite directions here. This is just kind of another example showing that this is something you might often come across. And so what we have here is that around this double bond, this bromine is the higher priority than this because bromine has a higher atomic number than this carbon. And this is the higher priority than the single H that will be coming off of there. And so this 3rd carbon right here is Z, so we put a 3Z there. But then we get to this 5th carbon right here. And so now this carbon going down this way is higher priority than this hydrogen, and this carbon is higher priority than this hydrogen. And so this 5th one is actually E, so it's 5E. So we have 3 bromo, this is bromine on the 3rd carbon, 3 bromo, 3Z, 5E, octa because it's 8 carbons long, diene because there are 2 double bonds on here. But yeah, that is sort of how we go about this this EZ nomenclature. So now we can get into a little bit more of the chemistry here, other than just naming things, which is, naming things is very important, but, it can get a little bit tedious and there's a lot to sort of memorize. So it's not, it's not something that's like terribly interesting to a lot of people, I don't think, where if you're into chemistry, then you're probably more into the actual chemistry and reactions and thermodynamics and things like that. And so now we can look at the double bond stability. All right, so we measure the double bond stability with the heat of hydrogenation. So hydrogenation is adding hydrogen and using a platinum catalyst to what's called unsaturate these bonds, or to saturate these bonds rather. So the double bond is unsaturated because it's possible to add more hydrogens, where the single bond is considered saturated because you can't add any more hydrogens to it. And so you may have seen, things like partially hydrogenated vegetable oil. And so this is essentially what they're doing. They're trying to hydrogenate it because these alkenes are going to have like lower they're going to have like lower melting temperatures, so they're going to be liquid. And so when you want to make like sort of a fake butter, you take vegetable oil, which is a liquid, you hydrogenate it, and then it turns it into a solid. And of course, this is with oils, which are different than just pure hydrocarbons, but they do have a hydrocarbon chain, and so it's this reaction that's actually happening to those when they are partially hydrogenating it, meaning that they're turning it into a saturated fat. But anyway, my biochemist is starting to show here, and I'm sort of getting off topic. But anyway, we're going to measure the heat of hydrogenation. And so when we heat this 1-butene, or this but-1-ene, with this H2 and the platinum catalyst, we're going to our delta H of the reaction here is going to be negative 126.8 kilojoules per mole. So this is an exothermic reaction. But then when we do it to the trans 2-butene, or but-2-ene, whichever naming convention you want to use to make butane, this is the negative 115.5 kilojoules per mole. And so it's still, this is still an exothermic reaction. So if we look at this, what we see is that the trans-2-butene is more stable, so it's giving off less heat, which means the bond contains less energy. Bonds with less energy are more stable bonds. And so if we are giving off less energy when we go from here to this or here to this. So we're going to the same product in both cases. So that's how it's measuring sort of the stability of the bond by looking at how much heat is given off when we go to the same product in both cases. And so this trans-2-butene is more stable than 1-butene by approximately 11.3 kilojoules per mole. And so then if we add a substituent on it, so now we're looking at the same thing, but now we're adding this methyl group onto it. So now we're looking at 3-methyl 1-butene and 2-methyl 1-butene. And so the naming convention here. So on this one, we're going to start here with 1, 2, 3, 4. But this one, this double bond is right in the middle, so we will start from the end that's closer to that substituent there. And so that is why the naming is that way. But we're performing the same reaction, and now we see that this here is negative 127 kilojoules per mole. This is negative 113. So this one is the more stable double bond than the other one. And it's more stable by 14 kilojoules per mole. So by even more than this one right here. And so what we see is that ethene, so it has no substituents, it's just hydrogens around that double bond. It's about 137 kilojoules per mole. When we have a single substituent, it's around 126. When we get to two substituents, it's between 116 and 120. Then we get down to three substituents, which is what we have here. So we have 1, 2, and 3 substituents for that negative 113. It's around 112 kilojoules per mole. And so this is where we get what's called Zaitsev's rule, which is that the more substituents there are on a double bond, the more stable the double bond. And so that's what we see up here, where up here this has just one substituent coming off right there. This has two substituents coming off of it. Again, this has just one, which is why this is approximately the same as this. In fact, this one is probably just the same number, but they just rounded it up from the data that I found for it. Where this has 3 substituents around it, and so it's even more stable right here. So we can look at this table here, which is just looking at a lot of these structures. So we start with ethene up here, which has no substituent, so it's unsubstituted. And so we see this has it at around 136 kilojoules per mole, where this column is in kilocalories. But then as we go down this, we are adding more and more substituents. So this is 1, 2, this is 2, 2, and 2, but this is looking at the cis, which remember is that they're both on the same side here. We have geminal, which is that they're both on the same carbon here. Then the trans, which is that they're going in opposite directions here. So those are all di-substituted. Then we get to tri-substituted and tetra-substituted. We see that the energy here as we go down this is decreasing, so they're becoming more and more stable. And so we can look at this little graph over here, and so this is comparing the energies of these two ethylene. And so when we have the mono substituted, we are down by about 11 kilojoules, as we saw from above. Then when we're di-substituted and we are cis, we're at about 18 kilojoules more stable. Then geminal is 20. Then we get up to trans, which is 22. So we see that the trans is more stable than the geminal or cis. And we could see that because there is going to be some steric clash between the R groups on here and on here. And so that's going to make those a little bit less stable. So this trans is actually more stable. And so this actually gets back to uh, I was talking about before about like the partially hydrogenated like vegetable oil. So when you're undergoing that reaction, sometimes you can break these bonds on these cis, and then they will usually go to this trans. And so that's actually where you get trans fats from. So if you've ever heard of trans fats, like a lot of these fake butters and stuff like to say that they don't have trans fats because they probably did something to remove it or something like that after they've made them. But anyway, again, my biochemist is showing through and I'm getting off topic. But anyway, so yeah, the trans one is a little bit more stable here. Then we have the tri-substituted, which is even more stable, 25 kilojoules more stable than the tetra-substituted, which is about 26 kilojoules more stable here. And so that is the stability of the double bonds there. So cyclic alkenes, so with these, uh, I'm not going to repeat everything I said because most of the same things will apply to these as what we were talking about with the linear chains. So they mostly behave similar to the linear alkenes, but there are a few notable exceptions here that I will point out. So cyclopropene, which remember is just that sort of triangular shaped one, but now we will have a double bond on it. So it's triangular shaped, and one of them will be a double bond. And our cyclobutene, which I already have the structure for right here, have even more ring strain because they are now sp2 hybridized. So remember, I was saying in a previous video that when we have these here, so I showed that graph that had like the square on it, and then there was something that looked like this, and there was that little bit of extra angle here that the bonds actually want to go to. So this is a 90-degree here, but they want to get to 109.5, and so there is a 29.5 degree sort of collapsing of this when we try to make this square structure here. And so that puts some strain on that bond because the sp3 wants to be 109.5, but now we are at sp2 and these want to be even greater. These want to be 120 degrees, and yet we are forcing it into these 90-degree things. And so the bond angle is compressed even more compared to what it is supposed to be. And so the same goes for this, which had the 60-degree bonds. Now they want to be 120 degrees. Um, and so these things are like extremely unstable. They will usually break apart even at room temperature. I think you can store them at like really cold temperatures, but they're quite unstable. I think for a while people even thought that something like this would be impossible. I believe it. In fact, I know it has been synthesized since then, but for a long time it was believed that it would be impossible to even make. And I think there's actually a plant that makes something that contains one of these rings. So a chemical that contains one of these rings, and they can act as like an inhibitor of certain enzymes in the body, so it can actually be quite toxic. But anyway, the other thing I wanted to point out, and this is something I already touched on before, is that cyclic systems with fewer than 8 carbons that also have a trans double bond are extremely unstable. So we can see here, this is an 8 carbon ring right here. And so this is the trans double bond. And this is in sort of two different conformations here. So we have the double bond. We see that it's sort of bending this ring all different ways when we are in these two different conformations. So if we tried to bend a like 7, 6, or 5 member ring like this, by having these trans bonds. So remember, it's trans, so this is sort of coming off of that double bond in the opposite direction of this other high priority one. You can also see it with the low priority, this hydrogen coming off in the opposite direction of that hydrogen. So that is also true of it. But you can see that if you try to do this with fewer carbons, you're going to start, you know, having a lot of ring strain, and it's going to become very unstable, and so you don't actually see that very often. In fact, I don't know that they can exist at like room temperature. All right, and so the last thing I wanted to talk about here is actually the polarity. And so alkenes are slightly more polar than alkanes because, and sort of the big one is more weakly they have these more weakly held electrons in the pi bond that are more polarizable. So you can think of, I was using this in a previous video, that the electron can sort of slosh around in these bonds a little bit more, and so there can be a little bit more polarity on them. And we can also see that these vinylic bonds are more polar, which is what we see here. And so we have this carbon right here. So this was actually supposed to be a carbon, CH3 right there. So that should be a CH3. And so this is the trans 2-butene. So it's 1, 2, 3, 4 carbons. So that's the trans 2-butene or the trans but 2-ene, whichever way you want to call it. Then we have the cis 2-butene here. And what we see is that the vector sum of these dipole moments on the trans is going to be 0, where on the cis it's going to be 0.33. And we can actually measure this with a slight increase in the boiling point of the cis as compared to the trans, where this boils at 1 degrees Celsius and this at 4 degrees Celsius. But this is even more pronounced when we put some chlorines on here. And so so the dipole is sort of in this direction, so there's going to be a partial positive on these right here, where now we are going to have a partial negative on these. The dipole is going in the opposite direction. And so with the trans, so this one is going to cancel out with this one. When we do the vector sum, we get 0 on the dipole moment here, and the cis, we get a 2.4 on it, which is quite large. And so we can actually measure this with the boiling point, where for the trans here, it's 48 degrees Celsius, where on the cis it goes up by 60 degrees Celsius, and that's because we're going to have these dipole-dipole interactions in the liquid here, and so that's actually going to make it. It's actually going to increase the boiling point because there's going to be stronger interactions within it. So if you watch my video on the properties of solvents, you'll know that the dipole interactions are atom per atom stronger than like the van der Waals forces, which are going to be the major contributor on this right here, which has a vector sum of 0 for its dipole moment. But anyway, there is more to say about alkenes. This isn't the end of the chapter on alkenes, but this was the stuff I wanted to sort of touch on before we started talking about some actual chemistry stuff, some reactions and things like that, which, like I said, do start. So the book does start talking about like reactions on double bonds before it goes into this kind of stuff. So I kind of wanted to get this out of the way with first. But anyway, I don't want to ramble too long. This video is already quite lengthy. So I hope you found this video helpful, and I will see you in the next one.